one thing. Can we switch off video on your end?
Okay, that's fine. That's fine. So
I
the
think
next, the
the bandwidth is quite low, so why don't we switch off our videos and then I'll share the screen.
okay, we will start. So the last speaker of the day is Patrick Chodari from University of Pennsylvania, and his talk is related to learning and thermodynamics, is learning with few labeled data. So the floor is yours.
Yes.
Okay, that's fine. You hear me? You could start.
Yes. Yeah. Okay. So I hope all of you can hear me okay. I think there is a lot of lag between me speaking and then you getting it. So can we switch off the video? I will switch off. Uh, I will keep my video on, but maybe you can switch off the video on your end. Okay, that might be better. Hopefully, so I will monitor the chat here. So let me know if you cannot hear everything nicely. But okay, so okay, that might be better. I'm Chodari. Uh, so I am a faculty at the University of Pennsylvania. I couldn't be there in, but I wish I had been there. Thank you for letting me talk virtually. Okay, let me close my camera. So I will talk today about how to do machine learning with three parts. First, I will give you a short introduction of what neural networks are, of how we typically use them, or some of my older. Uh, okay, let me close my camera. We'll talk about some algorithms that do particularly well when even if you have say one samples or five samples of label data, which is an important problem for formalizations of these algorithms. The algorithms, the second part, that tell you what are, there will be some allusion to thermodynamics here, some allusion to stochastic processes, and we'll get to it when we. Okay, so for the purposes of this talk, neural networks are very simple objects. Of what neural networks are, on the left hand side, you have an image that comes in, and you apply a sequence of transformations to this image. So each of these boxes is let's say a linear operator. Between each of are operators that people like to use, which are thresholding, set everything that is negative to zeros and leave all the activations that are above. We have other such non-linearities, and a typical deep network consists of a sequence of such linear operations interleaved with nonlinear operations. Out comes on the right hand side a vector. This vector typically is of two classes, cats and dogs. The length of this vector would be 2. And we choose to interpret this vector as a probability vector. So I plug in an image on the left hand side, and the network tries to predict how likely it is that this image is that of a cat. When the network starts performing well, you will see that so for the purposes of this talk, neural networks are very simple objects. Probability mass given to dog with is mistakes. Now, this is a complex problem, but formally speaking, the parameters of the network. These networks, the entries in these linear operators or the nonlinear operations that may also be parameterized as parameters. And when we say we want to train a network, we really want to find the best parameters that minimize some objective. This objective is computed as the sum over all your samples. So let's say if you have capital N samples in your training data set, then you would like to minimize the mispredictions of your model, which is denoted by this function f sub I. It is parameterized by theta again, across all your ground truth annotations. Now, there are a few reasons why this problem is challenging. It's challenging because typically you have a very large number of samples in your data set. So n capital N is of the order of millions. It is a huge sum. A lot of rich representations that you learn from large amounts of expression. The f of theta also needs to be very complicated. You cannot learn complicated concepts with simple functions in a very formal sense. So you want f to be a powerful function, non-linear, a highly non-convex function. That is what makes finding the best theta so difficult. This is a large scale non-convex optimization problem, and and what you will notice is that there is an algorithm called stochastic gradient descent that tends to work extremely well for this problem. So SGD at its heart is just a simple set of updates. So at each time t, you take your original parameters theta t, you don't take all the capital N so you want f to be a powerful function, non-linear images that you have or capital N samples you have, you choose some subset of B samples from your data set, and then you evaluate the gradient only on those B samples. This is what is called a mini batch, and you take a step in the direction of the negative gradient. These subset of the samples, the mini batch, they are sampled, let's say, uniformly, randomly from your data set. I don't really care about estimating the gradient of job, even if I choose, let's say, want an algorithm called stochastic gradient descent, and it works spectacularly well in spite of you solving the problem of this time. In fact, if you see most neural networks that have come up in the last, let's say, 5, 6, 7 years at this point, how well they perform, how big they are, how complicated they are, these architectures become more and more complicated over the years. This one single algorithm was used to train every network on this plot. And that is very surprising. So because it is an algorithm that is not even known to this is an algorithm called stochastic gradient descent, and it works spectacularly well in spite of all. In fact, if you see most neural networks that have come up in the last, let's specific form. So why should why should an algorithm that would easily be considered among the worst algorithms to minimize a function work so well? Results focus on why is SGD so special. If you understand something that is special inside SGD, can we improve it in some sense? Is this really the best algorithm? What this plot shows is that it is very simple. So I took the large summation in the objective. I trained a neural network for some time, and I'm computing the hash that tells you how curved the function is. And I am plotting the eigenvalues of the Hessian. What you will immediately notice is that a very large fraction of the eigenvalues that I have trained, about 95% of the eigenvalues, are essentially zero. There are a few positive eigenvalues with varying orders of magnitude, and there are a few negative eigenvalues also, not too many, but a few. So typically, by the end of training, but saddle points because they both have negative eigenvalues and positive eigenvalues. But the most drastic actually zero. What this means is that you've reached a space in the parameter space. You found a value of theta such that no matter which direction you look at locally, minima colloquially in the literature, they are not really minima. They are wide in a very different sense from the Hessian. And what we notice is that every single time you tend to do a good job of machine learning in the sense that your network works well on new data. It just if this peak is not that tall, if this peak is let's say 10 to the 3, then the the performance or drastic aspect of this figure, new data is not that good. And this we discovered in experiments. And now the question is very simple, right? So you know that SGD finds regions like these. So why don't we go for a loss function like this does? So objective f of theta, which is the summation that we wrote on the first page, and you exponentiate it with a negative sign. So you haven't done anything yet. You simply make it more rugged. If f of theta was non-convex, then e to the negative of theta is more drastically non-convex. But then when you smooth it with a Gaussian kernel, so G sub gamma is a Gaussian kernel of variance gamma, you get something that is if G sub gamma was identity, then you would simply be computing the log partition function of of your energy. Lets you compute a local free energy. This is computationally nice and network now. This objective, because of the smoothing, it destroys all parts of the parameter space that are very curved. Okay, so this objective is called local entropy, and turns out local entropy is a very good objective for training neural networks because it has this flavor of destroying all regions in the parameter space that don't belong to it. So it's a very good objective for training large neural networks using these ideas, and some of which we did. Focus on the black line here, for a typical data set cursor far with a typical network. Let's not worry about what that network is. The purple line or the blue line are these are to compute a local free energy. This is computationally nice, and it also gives you an objective that okay, uh, okay, the parlay which trains the neural network using local entropy, and even after okay, so evolution it is so much better than stochastic in this. These algorithms also tend to work really well for situations where you don't have too much data, simply because they come from something called as a replica symmetry and a large replica of models together in synchrony. You can understand the purple line or the blue line are this results a little algorithm that kind of starts at a location and then goes into a ditch, a local minimum. But as a stochastic process, the amount of time, and then ask ourselves the question: what is the distribution on the parameter space induced by this stochastic process? And this is the kind of analysis that we did. We wrote down a continuous time stochastic differential equation that is a model for the you can show a result that goes as follows. So SGD has a non-equilibrium steady state distribution, and if you kind of write down the variational forms, you will get an objective following form. So rho SS here is a distribution on the weight space well for situations where you don't have to induce by SGD at the end of training. This is a complicated distribution, but using ideas like in variation inference or optimal transportation, you will get an objective of the following form. So the final distributions row of a sum of two terms, wherein there is an entropic term that really comes because you are sampling the data each iteration with an entropic bias that tells you that the distributions that SGD finds are as entropic as they can be on some, let's say, compound. The reason is that the first term is not the classical Gibbs energy. So you are minimizing a function f of theta, but f doesn't show up in this formula. What does show up is a different function called phi, and you can prove that phi and f updates of stochastic descent that is on the first slide, and RX SGD satisfies detailed bounding. That really means that stochastic gradient descent, if it has noise that is highly non-isotropic, hierarchical architectures and the datasets that we use tend to give you a noise in the gradients that is very non-isotropic. So the Markov chain underlying SGD has is draft function phi of theta is quite different from the function phi of theta that is f of theta. So gradient steps to minimize this function, but because of the noise in your updates being pathological, roughly speaking, you end up minimizing a totally different function. Your critical point. One way to kind of dig deeper into what these kinds of results before non-isotropic noise. But having said that, the problem is really that when you study neural networks, there are three things going on, roughly speaking. You pick an architecture. The one that we showed on the first slide is one typical architecture. There are many others. New ones come out every day. We call them, let's say, SGD. And then we get some performance on new data. That new performance and how to get good performance on new data is entirely unclear in the current scheme of things. So whether I should pick a new things interact with each other quite badly, and it is all a bit decision, and then we want to do that on new data. So even if SGD is an old algorithm, optimization using SGD is a very, very well understood concept for other machine learning models, let's say linear one, and way very difficult to characterize it for neural networks. And these flavor of results tell you one story of how one may model studies problems. The key to understanding neural and data is the one that gives you this non-isotropic noise, and if you don't understand data, then there is no hope of understanding where this noise is coming from, or why you are doing it. So that is what began this work on to you briefly. So roughly speaking, at least in the industry, or engineering wise, we are very good at training neural networks. If you give me, let's say, 100 samples per class, give me 1,000 samples, in my data set. If you have 1,000 classes, give a million samples. And this is what is called the high shot regime. And we, even if you don't understand how to train networks robustly, it doesn't work well in practice. 10 samples per class. Imagine, let's say, a farmer in California who a machine learning model for classifying his strawberries. Now, it's not as if he has the time or an enterprise to collect 1,000 images per kind of strawberry for you. Uh, what he would like problems that we are not good at solving yet, and the trick to solving these problems lies in relearning the network using and then adapting this network to this new problem. Let's say strawberries or oranges or some field that is called transfer learning, which is what we're going to talk about. We won't talk about the look of the they're typically called exponential universe classification, depending on which field you come from. Can a neural network identify an image that rise? We are very good at training neural networks. The way you build neural networks, you partition your entire universe into 1,000 classes or 100 classes, and the network really has no idea of anything outside them. So it no, even if I show you balloon at test time and you haven't seen them at training time, you will still classify it as one among the training categories. Let's try to formulate the problem of few short learning. The problem is that I would like to collect a lot of data from frequent on the internet, and I would like it to do well on strawberries. And the way I'm going to measure how well I do about ways, so W is 3 images per class. So S is the number of shots. I may give you 5 labeled images, I may give you 10 labeled images, but few. The trick it is up to 10. And you would like to do well on these new classes by training machine learning, where the classes at training time and kind of algorithms that tend to work well. Like if your objective is classes, then uh, on classifying current classes. So you simply want to learn to distinguish between two classes. So if you know that there are three kinds of strawberries, I'm going to take the training data set and then split it up into three classes in each episode, and then simply train my neural network to be good at distinguishing between three classes. At test time, it doesn't really matter because then it will also be good at distinguishing between three new classes. This is what is called this is a way I'm going to measure, give you three kinds of strawberries, the networks, and the trick lies in simply saying that I don't really care about classification, I care more about clustering. So if I give you new data to classify, I decide which class it belongs to simply by looking at which cluster, which centroid it is closest to. And here is how one can form a very formal sense is a function f, capital F, that is trained on a dataset ds y hat given a datum x that we are supposed to classify. Now, in principle, you are allowed PDF. Why don't I will use Zoom to share slides, but I will use my phone to speak. I think that should work.
No. I prefer to display the slide and you speak in the phone. Okay. So we are in the slide 19.
Okay. The information bottleneck principle.
Which one? Which slide? Which?
I don't think this is going to work because I don't know which slide you are on.
No, but give me. We have stopped. We have stopped. We have been deconnected at slide 11. Could you start at slide 11?
What is the title?
Slide 11.
Can you tell me the title, because there are multiple slides with numbers.
Problem formulation.
Okay, I can start with problem formulation. So let's try to formulate the problem of few-shot learning, and it goes as follows. So you collect data from frequently occurring classes, such as cars, cats, dogs, and planes, and you would like to classify new classes, let's say strawberries. Now, the hard part of this is that I give you W ways of W different types of strawberries. So let's say W equals 3. And I give you only one or two labeled examples per new strawberry. So this is what is called a shot. In few-shot learning, the number of labeled data that I give you for the new class F is small. Next slide, please.
Okay.
So here is one kind of algorithms that we will talk about. These are what are called prototypical networks. And the key to understanding this is simple. So if you know that you're not going to be tested on the same classes that you trained on, then you don't care about classifying the training classes. What you do care more about is simply discriminating between a few training classes. So you chop up the world and you train a model for clustering as opposed to classification. If you see the figure on the bottom, there are 3 classes, C1, C2, C3, and each of them has about 4 samples that belong close to them. If you manage to cluster...
What is the title of your slide? What is the title of your slide?
A flavor of current few-shot algorithm. Okay. Why don't we use Zoom for slides? I think that will work because there is no bandwidth there.
Okay, that's fine. No, I display the slide from my laptop, but give me the title when you change slide, okay?
Yes, yeah. So the title is a flavor of current few-shot algorithm. And as I said, instead of training a model for classification, you want to train a model simply for clustering. That is what prototypical networks does. The next slide is the key idea. The key idea simply relies on the fact that in machine learning, you're supposed to find a classification function, capital F, that classifies the data. Now, you won't be doing a good job of learning the classification function F if you don't have enough data. You are going to use the parameters theta star. So can you advance to the next slide? You're going to use the parameters theta star to create a statistic of the training data set. And these parameters will help you classify new images quickly without having to search over all your functions F. This is kind of machine learning 101 in some sense. Instead of maintaining a classifier, we choose to do the search a little more explicitly. And this is necessary, which you cannot learn a classifier accurately with few data. So can you advance to the next slide?
Give me the title of the slide. Give me the title of the slide.
The title of the slides is constant across a large number of slides. So that is, this anyway this will work if we synchronize using the title. We should synchronize using the page number of the PDF, but that is difficult to do if you do the full screen.
No, but give me, yes, there is some animation, but just give me the slide, the title of the slide on it. It's enough.
The
Yes, I know, it's just animation. So we are in the slide, a very simple baseline.
Okay. Yes, so let's try to take it redo this. So here is a very simple baseline that you can build for two-shot learning. You train a large neural network on your training data set, and you simply run a classifier head. You add a new layer that is called the classifier head to classify these new categories. This is very easy to do, quite standard. And then you simply train the network, the entire network again. So this instantiates the loss function that we talked about, which combines the training data that you have in terms of its statistics and a very explicit fine-tuning or a search over the class of functions that help you classify on given access to unlabeled test data. Can you go to the next slide with the picture and example?
Result on benchmark?
No, there is a picture. It says an example, the one behind it.
We have got the same version of the slide.
How about we do this, Frederick? I think it is about 1 o'clock. So it is about to end. I will record a video and then send it to you. Is that better?
No, we have no connection with US. It's very difficult with Zoom.
No, I will record the video in my home, and I will simply send you a link to the recording, which you can upload. Because I don't see this working out.
Perhaps could you take the last version of your slide you send me first? I have not downloaded the last one.
Are you connected to the Zoom?
No. We cannot connect with Zoom. We cannot. It's disconnect too much. The connection is not good enough.
Here is what I propose.
Use the last version of your slide. You send me this week, but not the last one. I have not uploaded the last one.
Yes, so I will upload these slides to you, and I will send you a video.
I have no connection, so. Yes, if you want. You have the Zoom connection? I think you have a problem with the US connection. In Japan, you have no problem. In Japan, it was perfect.
Yeah, the problem with the connection on that side.
On that side.
Yes, because, yeah.
Can you tell him to send me an email? You have his.
Yeah,
try to share the screen now to the slide.
Can you see?
Yes.
So let's.
Can you hear?
I will call the phone call.
I can hear you. We can hear you. Yes, yes. It was okay. You just have to share the screen. Now you're not sharing anymore.
Now, can you hear? Can you see it? No.
No. At a certain point, it was working. You have to click on the
Okay.
button.
Yeah, 1 second, 1 second.
Yep. Yes. Oh, yes.
Okay.
Good.
Okay. Let's do this. I will start from here.
Okay.
Okay. So essentially, I'm sorry for the interruptions. I don't know what is up with the bandwidth. It is way much better than this usually. So sorry. I will try to record a video separately and then send it so that it is more polished. I will not keep you long from your dinner too much. We'll talk only for about 15-20 minutes, and I'll give you a flavor of some formalization of our work about transfer learning. And here is how it would start. So you people might have heard of rate distortion theory in information theory, and the information bottleneck principle, which was kind of started by Naftali Tishby in the late 90s, is a generalization of rate distortion theory, and typically it is thought of as follows. So if I have data X and I'm going to make some predictions Y using this data X, in between, I would like to learn some representation of the data. Think of it as the features of the data that you learn, the convolutional filters, the activations of the filters that the network learns, whatever you like. What kind of representations X we want? We want representations that are sufficient to predict the target Y, in the sense that if I throw away the data X, I can still do a good job of predicting the labels given access to the representation. This is the definition of a statistic. We also like statistics that are small in size. So in the sense they are small in the number of bits it requires you to store them. For instance, JPEG is a more efficient encoding of your images than PNG. JPEG images are smaller than PNG images, so the JPEG is a smaller representation. When you learn such representations, this is what machine learning would be formalized as in some cases. You would like to use the following loss function. The first term is a minimization of the mutual information between X and Z. What that means is you would like Z to throw away as much information from X as possible in the effort to make Z small. You cannot throw away everything, of course. You would like to maximize the mutual information between Z and Y. And that really tells you that Z should be maximally informative about predicting Y, and you should be able to do a good job of predicting Y, even if you've thrown away information about X. This, in a nutshell, is what would be called parsimonious feature of machine learning models, um, or minimality of the statistic. And the simple reason why people do this is that if I give you images of dogs on grass, I don't want the machine learning model to focus too much on the grass, because the next time it sees a cow on top of grass, it is going to call it a dog. This is what is called overfitting, and making the representation minimal or in size certainly helps you prevent overfitting. Now, the key point and the key idea of transfer learning, what we talked about in the the previous part of the talk, is that doing well on one task, so doing well on classification of the frequent categories or classification of dogs, requires you to throw away a lot of information about this task. If you throw away a lot of information about the task, you don't have enough redundant information to do well on a new task. So when you adapt machine learning models to new tasks, there is a very clear tussle, a fight between doing well on task one versus learning a lot of redundant information on task one. If you learn a lot of redundant information of task one, then you're not going to do well on task one, but you will do well on task two. But if you do well on task one by throwing away lots of information, then you have nothing to use when you try to classify task two. So machine learning, the way it is formalized in information bottleneck or rate distortion, which is a very natural formulation, so speaking, goes against what transfer learning would like to do, which is to learn redundant representations. And this is exactly where we modify it. So you want one way to measure how much information is being discarded from your data set. And you can simply use another task to measure this information. So what you choose is you choose a canonical task. Let's say reconstruction of data. You simply set y to be equal to x. So you train your representation not only to classify your images, but also to be able to reconstruct the images back. And classification is a special task. It is the superset of all tasks and forces your model to learn lossless representations. The architecture we will focus on goes as follows. So you have your data X. It goes through an encoder Z given X, which is Z here, which goes through a classifier C of Y given Z into Y. And you use a decoder which tries to reconstruct your data back simply to measure how much information Z retains about the data and how much information Z retains about Y. So think of the decoder as a way to, as a thermometer, essentially. And now you can kind of analyze this model. This is what is called an autoencoder, a variational autoencoder, the way we use it in theory. Distortion, D, it measures the quality of reconstruction. It is simply telling you how good your latent Z is in order to reconstruct the data again. So logarithm of D of X given Z is the likelihood of your datum X given your representation Z. Higher the likelihood, the better the distortion. The better the reconstruction. So small d means that you're doing good job of reconstruction. The rate is what people in information theory would be familiar with. This is simply the number of excess bits that your representation Z encodes about the data X. If rate is very large, that means you're memorizing the data and you do well on distortion. If rate is very small, that means you forget a lot of your data and you won't be able to do a good job of distortion as well. Now, array distortion theory focus on the picture on the bottom. That really boils down to plotting D on one axis and rate on the other axis. And what you can show is that there is a very clear trade-off. So focus on the red line of models that can achieve good distortion or good rate. You cannot do both. So for instance, it's very hard for you to be close to the origin on this particular picture, achieve both good rate and good distortion. Either you get good distortion or you get good rate. And there is this red line, there is the threshold beyond which you cannot reach. So it is the fundamental limit of all models given a fixed capacity of rate and distortion that they can achieve. What we do in our effort to understand transfer learning is modify this Lagrangian to also include the classifier in our model. The classifier is simply the loss that measures mispredictions of your model. And just like you have rate and distortion in this trade-off, you now also have another functional, which is the classification error. And just like you had a line on the previous slide, you now have a surface of functionals that you can think of as the reachable space of the representations given your model family, the neural network, and your data set. So every point on this surface is a function, let's say f, parameterized by two parameters, lambda and gamma. These are simply the dual variables corresponding to distortion and classification. And when you start training really is modeled as you starting somewhere outside the surface, following some non-equilibrium process, namely SGD, and then falling onto this surface, which is the surface of the equilibrium free energy, where you've obtained a good representation given your current Lagrange multipliers lambda and gamma. Now, this surface, the way we think about this, is simply a constraint that ties together rate, distortion, classification, maybe the entropy, if you wish to understand it also, simply in one particular form. And it is very similar to what you would see in, let's say, the first law of thermodynamics, where the KKT conditions for this surface really look like a constraint that says that information is preserved in this particular model, the encoder, the decoder, and the classifier. Either the classifier likes this information and forces the encoder to learn it for it, or the decoder likes this information in order to reconstruct it, even though the classifier may not need it. For instance, the grass. So just like energy is conserved in physical processes, information is conserved in this model, and it's a very natural construction in some sense, nothing special about it. What it allows you to do is learn all possible representations given a particular family. So in this particular paper, we devised stochastic processes that traverse the equilibrium surface. So it's an equilibrium stochastic process that starts from, let's say, one point f of lambda 1 comma gamma 1 and tries to go to this other point f of lambda 2 comma gamma 2 while understanding certain constraints. For instance, you may have a constraint that says stay on the surface, which is given by this quasi-static condition, and also maintain the classification error to be constant. So dc by dt equal to 0. And that's very powerful because now you have a way of traveling on this surface. You know that this surface is the optimal surface of representations because every representation that you choose to learn is some point on this surface. You can modify your representations while keeping the classification error constants or really any other functional that you wish. For instance, if you're doing Bayesian learning, you could choose to keep C plus R constant along your stochastic process. And the nice thing is that because the parameters lambda and gamma are simply scalars, you can instantiate the stochastic processes quite easily even for large neural networks and large data sets. So, which is what we do, just essentially just take the updates for lambda and gamma using finite differences by computing the free energy. Uh, Now, the key point of this transfer learning business really lies in understanding that the equilibrium surface of models is a function of the data set. It is, and the model. It is not really a function of the training process because the equilibrium surface only exists at equilibrium. It doesn't matter which training process got you to the equilibrium. If you change the data set, the equilibrium surface changes. If you change the model family, the equilibrium surface changes. And in the context of transfer learning, what you can do is take a one source data set, let's say PS, and one target data set, PT, and interpolate between these two data sets. So in this case, we simply do linear interpolation. So think of it as taking the distribution of source data and then changing it to the distribution of target data slowly. You can do some other kind of interpolation. For instance, Wasserstein interpolation is also very easily possible under this formulation. And the crux of the matter is that you can still create a stochastic process that keeps the parameters on the manifold while preserving classification error. So it preserves the classification error between the source dataset and the target dataset. If you said that I have a model which achieves 95% accuracy on my source dataset, and I wanted to also achieve 95% accuracy on the target dataset, you can instantiate the stochastic process while modulating the dataset using the equation above to get a very controlled mechanism for transfer learning. This is a very novel idea because today the way we do transfer learning is that we train something on dataset 1 and we try to train it again on dataset 2. If it doesn't work well, you really don't know what you should do. So constraints like this, dc by dt equal to 0, help you do transfer learning in a completely controlled fashion modulo the capacity of your parameter family and how close the target data set is to your source data set. If the target data set is very close to your source data set, then you don't have to travel for too long on the equilibrium surface, because equilibrium processes are slow, and traveling for too long will take a very long time computationally. But if the two data sets are even reasonably close and your neural networks are large enough, you can do a completely controlled transfer. This we show this using some standard data sets, not very large scale yet, but this is an example that is very powerful. So this is a data set called CIFAR. It consists of some vehicles, 4 vehicles and 6 animals. And what we're going to do is train first on the vehicles and then adapt the same model to work well on animals. If you do what people currently do, which is essentially do a non-equilibrium process on animals that is initialized at the equilibrium process of vehicles, you will get a curve that is the blue line in terms of the validation. So in the beginning, your validation accuracy is very poor for animals, but then after you train, it improves, let's say to 80% in this particular case. The ISO classification process is doing very well on animals at the beginning, not on vehicles at the beginning, not surprisingly. And because they're interpolating the distribution smoothly between vehicles and animals, you keep doing better. This is not a surprise in the beginning, but the key point is at the end, you are doing much better than the non-equilibrium process, the blue line. So the control mechanism, in this case, dc by dt is not exactly zero, it is decreasing slightly because your accuracy is reducing. And but the key point is, if your network is large enough, you will be able to hold the constraint constant for reasonable values, and you know that your performance on the target data set is not going to be worse than what you desire. To summarize this, we talked a bunch in the beginning of the talk about algorithms that work well for very few samples. These algorithms are very simplistic, but they work well if you give them large amounts of training data. And this training data doesn't have to be the one that you're interested in. It can be stuff that is frequent on the internet. So long as you do a good job of collecting this diverse data set, you can use existing very natural methods to do well on new tasks. The second part of the talk was more information theoretic look into the rate distortion and classification surface that we've been working on since then. This is a more fundamental quantity in machine learning. And what we hope to do by understanding this is understand how regularization occurs for neural networks, and perhaps also understand questions like when is an architecture good for a given data set. The current architectures that we see working well in practice, they have been created by people by trying out a lot of different things. So natural selection of architectures, if you will. And what we would like is some functional that tells you, given this data set, given this architecture, are they well suited for it or not? And the RBC surface is potentially one way to understand this question. And if I wanted to um, give you one punchline to end with, we've been talking about big data for a long time, but then big data, doing well on big data is easy because if you don't have enough data, you simply get more data from the market and then train your model with it. It is little data that we need to worry about let's say, going forward, because there are lots of problems in medicine. Some of them we are tackling here at Penn, where you don't have enough data for all that covers all your test cases. You really need machine learning models, powerful ones like neural networks, to do well with little data, not just big data. And this is how this is the kind of algorithmic work that we are pursuing. And the theoretical work really boils down more into information theory and thermodynamics. We primarily talked about 3 papers. You can find them here. Please send me questions at this email address. I'll take questions if you have, but thank you for your patience. Apologize for the confusion and the low bandwidth across the Atlantic. Thank you very much.
Questions? Sorry? Okay, okay. Okay, okay. So thank you and sorry for technical problems.
No, thank you. Appreciate it.
Okay.
No problem.